Alright you guys, this is video E3.2-6, note section 2.2, earthquakes release energy. Again, we're looking at the learning target that is explain how scientists infer that the earth has interior layers with specific properties using the patterns of primary and secondary seismic wave arrivals. So we're just really getting into now what the heck are these seismic waves. So you should be looking at this. I'm going to minimize that and open PowerPoint. So number one, and again, use that pause button if you need to. Energy released by an earthquake travels outward in all directions in the form of seismic waves. This should make sense. Wherever that beginning point of the earthquake is, it's going to go up, down, left, right to all the sides, sending that energy in all directions, 360 degrees. All earthquakes start beneath Earth's surface, and this point is called the focus. It's underground where the rocks first begin to move. So the focus is where the earthquake starts. It is underground. It's where the rocks are first moving. The epicenter is actually the point on the Earth's surface directly above the focus. The epicenter is what we always hear about, like on the news and stuff, because it helps us locate atoms. We're familiar with the surface, not the subsurface. So if we said the epicenter was 5 miles north of, downtown Los Angeles, that helps us a little bit. So the epicenter is on the surface directly above the focus. And remember that focus is underground where the earthquake started. Here's a little diagram of that. We can see the focus underground here, and that's where this earthquake began. We see these seismic waves going out in all directions. We can see they're going this way as well, and down, up, down, left, right, forward, backward, everywhere. Focus underground, epicenter on the surface. Number 5, the shallower the focus, the more damage this caused. Deep focus earthquakes lose more energy as the seismic waves travel to the surface. Whoops. So, the shallower the focus, the more damage caused, and this is why. If this focus is here and we have an earthquake, there's a certain amount of damage. But if we move the focus closer to the surface, oops, lost my cursor, a little closer to the surface here, that energy has to travel less distance to get to the surface to do damage on the surface. If it's traveling less distance to do that damage, it's going to pack more of a punch. Likewise, if this focus is deeper, we're going to have less of an impact on the surface because the seismic waves lost energy as they traveled all the way up to the surface from way down here maybe. So the shallower an earthquake, the more damage it's going to do. So waves and energy. What is a wave? Well, a wave is a disturbance caused by energy. Waves carry energy from one place to another. Waves only ever carry energy from one place to another. Even waves in the ocean, they're not carrying water. Energy is simply moving through the water. So waves carry energy. The medium is the matter or substance that a wave is traveling through. Okay, whether it's solid rock or water or molten rock or liquid metal, whatever. Excuse me. Wave speed, we have to understand that waves are going to travel fastest through the through a solid, then a liquid, and slowest through a gas. This is because in a solid, the particles are packed more tightly together. They are denser. And when one particle is vibrated, the closer the next one is to it, it can be vibrated quicker, and so on and so on and so on. In a liquid, they're further spread out. So when this one vibrates, it takes a little bit longer for this one to vibrate, and so on and so on. In a gas, they're even further spread out. So the denser the medium, the faster the wave is going to travel through it. And there's 3 types of seismic waves. We have primary waves. We just call them P waves. Primary because they're the first to arrive. Secondary waves, or S waves, they're the second ones to arrive. And then we have surface waves. And we just call these surface waves. We're not going to shorten it because we already have an S wave here. P waves are primary waves, S waves are secondary waves, and then we have surface waves. Our primary waves are the fastest. They get there first. They can travel through solids, liquids, gases. They can travel through anything. Okay, solids or liquids, really. That's really all we have to think about here. And they're longitudinal. Okay, that means they're kind of like a sound wave. They're pulsating through the medium, all right, in a sort of back and forth way. When we do the Slinky Lab, it will really help us understand this. Secondary waves are the second to arrive, travel at about half the speed of the P wave. But here's the catch. Secondary waves cannot travel through liquids. They can't travel through liquids. They're transverse wave. These are the ones that we think of as snaking up and down or side to side as they move. It's kind of like when we take that rope and we tie it to the handle of the door and we flip it, we see that wave travel through it. This is a transverse wave, and this is what the secondary waves are. The really important thing here, you guys, is that they don't travel through liquids. And we know that from seismic waves, and when we record them when an earthquake occurs at places all over Earth. Sometimes the S waves never get there because they can't travel through the outer core, which is liquid. Finally, we have surface waves. Just like the name says, they move along the Earth's surface. They cause the largest ground movement and therefore the most damage. They're the slowest, but they pack the biggest punch. They come last and they're doing the biggest damage. Alright, so looking at this, I was trying to explain that primary wave. Slinkies are a perfect example. If this hand kind of pushes in, we make this compression. It is then going to travel down and ultimately reflect back in this case. But it's the idea that particle motion is in the same direction that the wave is going. Okay, we see here particle motion is left, right in this diagram, and wave motion is going down and then ultimately back. Right? B, secondary wave. Here's the example I was talking about with the rope. Particle motion is perpendicular to the direction that the wave is traveling, to the right in this case. Particles are moving up, down when the wave is going to the right. And then these other two, C and D, a love wave and a Rayleigh wave, they're two different types of the surface waves. Okay, we can do the side to side or the up down motion of these surface waves. And we can see that this is why these are going to do the greatest amount of damage, because these kind of happen all at the same time. These love and Rayleigh waves, I mean. So seismic waves can be measured. We measure them with seismographs. They're always recording ground movement. And these machines record the earthquakes by drawing these groups of wiggles, sort of like the heart monitor machine at the hospital that you might be familiar with from seeing on TV or something. But the height of the wiggles indicates the amount of ground movement produced by the seismic wave at that location. Okay, so the wave is probably dissipated by the time it gets to a location. But we use separate seismographs to record side-to-side movements and up and down movements. All right, and this one here, it's going to record side-to-side movements. This one, up and down movements. And ultimately, this is what we would get. When an earthquake starts coming in, we get the P wave arrival. Comes first. S wave is a little more intense. And then, boom, right here we're getting those surface waves. And it says L for that love wave. We're getting some surface waves. Okay, that's when it gets crazy. To locate an earthquake, scientists use something called triangulation. Tri means 3. Right? So 3 steps are followed to locate the epicenter of an earthquake. 1. Find the difference between the arrival times of a P and an S wave at 3 stations. Each of 3 stations has to do this. The time difference is used to determine the distance to the epicenter from each station. The greater the difference in the time, well, the further away that epicenter is from my station. A circle is then drawn around each station with a radius corresponding to the epicenter's distance from the station. So, if I'm at station C and I say, okay, this was my distance, it's somewhere on this line for C. Well, I need at least 2 other stations to give me their data so we can figure out where this earthquake is. If B comes in and says, well, this is how far it is from me, they can draw this line around them. Well, then we know it's at one of 2 spots where our lines intersect, here or here. We had that 3rd station for triangulation, and station A says, hey, it's this far from me, and bingo, we have our epicenter location right here. So basically data from 3 stations to find that epicenter. And that is our notes for this section.